Okay, thank you very much. My name is Kazu Suenaga. I came from Osaka University. First of all, I would like to thank Professor David Smith for giving me this opportunity. This is my first time to visit Arizona State University, and it's my great honor to join this Cowley Distinguished Lectures. I have to mention for the first, at the beginning, because this lab is quite respectful for Japanese people, because all the big names in Japan in our field are the apprentice of the John Cowley, and they spend several years in this university, and of course, and mainly from Japan, or mainly also from China. So this university is the kind of the holy place for us, and it's my great honor to visit this group and make this lecture. Okay, so first of all, I like to explain my career. Okay, so Dave has kindly explained quickly for my research career. So I started my PhD in the University of Tokyo, and then I moved to the École Nationale Supérieure de Mines de Paris, and also working in Technion in Haifa. At that time, I was a guy for the grain boundaries. Okay, so there are the big names of the grain boundary, and we used to work on that. So after that, I moved to the Christian Collect's lab in solid state physics in the University of Paris Sud. So there I learned the inelastic scattering of electrons. So I start to understand how the spectroscopy is important or interesting for such kind of experience, for our background. So then I was working on. Then I came back to Japan and working with Sumio Iijima. He's also the important person in Japan, and he was also the graduate of the Cowley's school. Okay, so today I'm going to, okay, so first I like to quickly explain where the Osaka is. Okay, so Osaka is it's a bit 500 kilometer away from Tokyo, and the atmosphere is completely different. I mean, it's really noisy and how can I say, lively cities. And if you have some time, please visit us in Osaka. Okay, so today I'm going to talk quickly what I have been doing. So the first, I like to make some overview of TM of nanocarbon materials. This is kind of my personal history, because since my PhD, I have been working on the carbon materials with an electron microscope. So this is I'm still continuing this experience. So I like to quickly show what I have been doing for this one. Then, so I like to make some small general introduction of the high resolution EELS. EELS means electron energy loss spectroscopy, that the electron can sense the single atoms, and we can get many information from that. Then I'm going to talk our most recent results about the spectroscopy for the low-dimensional hybrid materials, because it's very interesting, because the carbon materials becomes 2D or 1D or one molecules, all the electronic states becomes discrete, and the dispersion relationship becomes discrete. So we really need some high energy resolution to track all the electron states for the nanocarbon or hybrid materials. Okay, so yes, this is some image for me to show for my students for the beginning. So for TEM, so normally you can see the molecules, or you can see atoms here. For example, this is a kind of the nanotubes, and you have molecules inside. And you may see this black point is just moving out. So with this image, of course, you cannot say which element it is in this black ones. But of course, if you make some spectroscopy, you can get the information, and which you can make some elementary information from these heavy contrast metals. Okay, so this is, in this case, this is erbium. So you have one erbium atoms in the molecules. Okay, so then, so this is my postdoc work in 2000. So it was, I was in Paris, and I was using the Colloquium instrument, so that it was without aberration corrections, but we could make some spectroscopy for single atoms. So yeah, as you can see, so this black dot corresponds to the one atoms, and if you put, at that time our beam was around 5 angstrom, but if you just put the electron probe on it or off it, you can get some information of the chemical analysis. Okay, so in this case, if you put the electron on the gadolinium atoms, you can clearly get the signals of the gadolinium atoms. So this was the first demonstration of the single atom spectroscopy. That it means the electron spectroscopy can detect single atoms, but it was big drawback because we are using the 100 keV acceleration voltage, and in this case, one scan, all the molecules are destroyed. Okay, so of course we could get some signals, but all the molecules were already damaged. So this is my motivation to reduce the acceleration voltage to get some chemical analysis from individual molecules. Okay, so then. Okay, so how low we should go? So this is quite a simple calculation of the knock-on probability. So if you want to see the graphene, so you have to go less than 800. This is a knock-on displacement probability. So if you have the nanotubes or fluorine, you have to go a little bit lower. And if you really want to get some atomic information from the edge of carbon or graphene atoms, you have to go less than 35. So this is our goal. Okay, so if we could get some microscope that can sense one single atoms with acceleration voltage less than 35, so we could get informations without destroying the structures. Okay, so this is our starting point. So we have started this project in 2006. So the Japanese company named JEOL helped us a lot. So we call it a triple C project because we wanted to visualize and make some identification of single carbon atoms. And so we call it, so we are making some dedicated microscope for low voltage, and it is a CC, it's a chromatic aberration corrections, or CS correction, and for carbon materials. So this is really dedicated for carbon materials to visualize or to identify the single carbon atoms. So this has been funded since 2006, but now it's still getting some small money. And now I have just approved one new project. So I'm going to work on the CC corrector for probe in coming 3 years or 5 years. So this could be my last hardware during my research career in Osaka. Okay, then, so yes. Okay, this is a very simple figure because for optical microscope, of course, the resolution is almost close to the wavelength or half of wavelength. But for the electron microscope, the resolution is still very far from the wavelength limit. So the resolution is around 10 or 20 times of the wavelength. So this is because our lens is not good enough to realize the wavelength length limit. Okay, so then I'm quickly show what we are doing in our microscopes. So we are just, if you try to see the wall using the cup of the water, so only this flat face area can be used for the lens. Okay, so if you really want to increase the spatial resolution, not increasing, I mean, without increasing the acceleration voltage, you have to make it wider. Okay, so you have to make the flat region-wide. Okay, so then we have a very nice guy in JEOL because, okay, so this is the aberration of the microscope. So we have write down up to 5th order aberrations. And so this is the neon notation. So this, you have several different aberrations, but our microscope, now we are collecting all the aberrations written here, okay, up to C56. Okay, so just quickly show. Oh, okay, so then this is how our corrector works. Okay, so for if you don't have any aberration corrector, so it's only the maybe it's only 11 milliradian is a normal one, but if you have the 2 hexapole how do you call it? 2 hexapole correctors, you can get this spherical aberration. This is 3rd order aberrations, so you can get much wide. But as you can see, this longitgram, so you can have 1, 2, 3, 4, 5, 6. Okay, 5-fold 6. No, 5 order 6-fold aberration is limiting the resolutions. So it means our next step is to remove this 6-fold astigmatism. Okay, so we have very nice guy in Japan. This is Sawada, Dr. Sawada. He designed some new corrector to get rid of this 5th order 6-fold aberration. So he made 3 dodecapoles, and the 6-fold aberration, which was made by first and second dodecapole, can be compensated by the 6-fold astigmatism of second and third dodecapoles. So this will gives you the very nice, how can I say, very nice resolution, even you have low acceleration voltage. Okay, so this is what we made for the beginning in our project. So now, okay, sorry, there are some Japanese there. So once we make this aberration corrector, we begin to get the information. Okay, so even at 30 keV, we could get 1 angstrom resolutions. So it means we can see the carbon-carbon, we can distinguish carbon-carbon distance, atomic distance at 30 keV. As I said, 30 keV is less than the threshold for the knock-on damage. So now we can have this microscope that we could get some information from the carbon materials without destroying it. Okay, so we have low enough acceleration voltage. Yes, so and if you calculate that, this is 15 times of the wavelength. So it's still we still have something to improve. Okay, simple calculation. So this is a kind of the, how do you call it, CTF, the first 0. So if you go this is to the 1000 milliradian, in this case you can get the resolution of the wavelength limit. Okay, 1000. Okay, but still we have only 71. So it means we could get up to around 15 times of the wavelength limit. Okay, then then we use this microscope that we can get information from the carbon materials. Okay, so this is the comparison of our own images. So in 2004, we didn't have any aberration corrections, so we could barely see the hexagonal alignment of the carbon materials. But once you get some aberration corrector and you have the monochromator to reduce the chromatic aberrations, in this case, you can get very clearly the each carbon atoms. Okay, so this is, as far as it's big advance for for a long time. Okay, then I come back to the spectroscopy. So, so if you are working on a 30 keV, as I said, you don't need to destroy the molecules anymore. So if you try to put some one single atoms in a molecules and make a chemical map, so you have one lanthan atom and one cerium atom. Lanthan and cerium are very close in atomic numbers, but we can clearly distinguish in a chemical analysis. Okay, so and as you can see, for the carbon fluorine carbon molecules is not yet destroyed. Okay, so it means we are now really you can make single molecule chemical analysis without destroying it. So this is what we have been trying to. So if you compare with my own 2000 year the results at 100 keV, it's completely different. Okay, so we are now able to get some spectral from single molecules or even single atoms. Okay, then so this is my final example of my history. So if you have try to make some spectroscopy from single carbon atoms. Okay, so this is you can see the movies that you can. Okay, all the atoms, carbon atoms is not only the hexagons. You have some pentagons, or sometimes you can get some atomic chains like that. So this is different carbon allotrope, but you can make some. How can I say the spectroscopy from each carbon atoms there. Okay, as you can see, this is a kind of pi-Ls distortions. Okay, so if you have the one-dimensional structures, the carbon atoms cannot be in the same distance. They have some dimerization. So in this case, as you can see clearly, these two carbon atoms are dimerized. And then so you can make some, of course, spectroscopy at 30 keV. So, or in this case, so you can have some, as you see, the two carbon atoms are dimerized. And if you make some spectroscopy from all of these places, so green one is a normal sp2 carbon, okay, normal sp2 carbon. And the red, blue one is the edge carbon atom. So you have different places. I mean, the carbon K edge show another peak. So, and if you have the carbon chains, again, the pi star peak just a bit shift. But as you can see, we can get the spectrum from each carbon atom. So this is one of our goal for our first project, because now we are able to visualize carbon atoms and and make some spectroscopy. Okay, let me summarize what I have done for my research career. So my PhD in 1994, I have making some C60 crystals, and this lattice is just the crystal of the molecules. Okay, so at that time I have never been dreaming of visualizing the single carbon atoms at that time. Okay, so it was a dream. I mean, I couldn't dream about it. But for after 30 years, we start to get some chemical map, and then we begin to see the graphite lattice in 2004. And in 2007, we begin to see the molecular structure of the carbon allotrope. Then 2010, we have, it was my operation at that time, we have succeeded to get the spectrum from carbon atoms at the edge of the graphene. And then 2017, so we have finally get some spectrum from each carbon atoms of the atomic chain. So it's very surprising for you probably, because I have been doing the same thing for more than 30 years, because I didn't change my topics, because but we are quite nice era, because I mean, detector getting better, the electron optics improved a lot. So for us, it's a big changes for these 30 years. So now finally, we have been able to get some spectrum from single carbon atoms. Okay, so I'm a bit too long for my first part. So I quickly go to the next step. So we could get some signals from single carbon atoms. Then we are trying to get information from the vibration of the colors. Okay, so for the carbon materials, it's very interesting because for one-dimensional structure, carbon nanotubes, it is the different colors. Okay, so if they have some different structures, the color becomes different. And of course, the graphene is also the discrete energy levels, but of course, it has some vibration properties. And of course, now we are getting more higher energy resolution spectroscopy to get information of the carbon atoms, not only the core loss, but trying to get information from the optical range or the vibrational ranges. Okay, then so now let me go about the introduction part. So for energy resolution, okay, so for energy loss spectroscopy, this is the basics I mean, this is my understanding. So if we have one atom, and if the electron goes very near the atoms, and the electron can be scattered, and the atom gives some how do you call it? To dielectric response, and then so you lose the energy. So, and we could measure this and the energy loss. Okay, so there's important things you have to understand here, because in the textbook, the energy loss spectrum is written as a loss function. Okay, so because electron can make many times, how do you call it, scattering, okay? But in our case, our specimen is very thin. It's only one atomic layer specimens. So in this case, the electron can scatter only once, okay? Only once at the most. So in this case, it's the same thing as X-ray or light. It's a kind of a kinematical scattering. So there's no need to think about the multiple scattering. Okay, so in this case, our spectrum is becoming epsilon 2. I mean, this is the same as a light scattering. Okay, I have to tell it again because it's very important. So the electron, if the specimen is very thin, the EELS spectra is no more loss function. It's just the absorption spectrum. Okay, so this is the important things. Okay, so then. So for the high resolution EELS, so we have at least a different direction to go. Of course, we have spatial resolutions on the left side, and we have momentum resolutions. And we have also the high energy resolutions. And for the last things that I have to think of is the time resolutions. Okay, we could go many directions, but of course we cannot get everything at the same time. Okay, if you take one resolution, maybe you have to sacrifice the other resolution. So this is the kind of the trade-off. Okay, then okay, so first let me explain about the spatial resolution. Okay, so this is an example that we could get some single atoms in single atomic chains in nanotubes, and you can get some chemical map for, in this case, this is cesium and iodine. Okay, so let me explain. So I will make the analysis here, if I could get it. Okay, yes, we could do it. So let me try to make some chemical map. So so this is on the EELS map. So if I put the beam on these bright atoms here, you can get the signal here. You can see that. So I hope you can see that. So let me make some chemical map of this. Oh, okay. Oh, sorry. Chemical map of this. It's command. No, option. Oh, sorry. I have to practice a little bit first. Oh, okay. I cannot do that. Okay, do that. So if I make this map, it's too much. Sorry. Sorry. 効率で I try to get it. Oh, I cannot get it. Sorry. こっちか。これか、これだ。Oh, okay, so it didn't work. Sorry. So, okay, I have to go like that. So, okay, so if we, okay, sorry. This is a chemical map that we could make from that spectra. But as you can see, so you can see cesium atoms and chlorine atoms there. So chlorine is a bit light, and you may not see between two cesium atoms. But if you make some chemical map, you clearly see that. But important thing is that the size of atom is different. Okay, so if you see the size of atoms in ADF map, but if you see the atom size of atom cesium, this is a little bit bigger, okay? A little bit bigger. So why it's happening? So this is the so-called EELS signal delocalizations. Okay, as you can see in other examples, so if you make some map of lithium, so the lithium map is very big, okay? So this is for the lanthanum and cerium, but they are a little bit bigger than the ADF map. Okay. So, okay, this is a point. So what I want to say is that we don't need to make smaller probe anymore because our chemical map is already dominated by the how can I say, the yield signal delocalizations. Okay, so this is the point. So if you have the one atom map, so ADF, cerium N or cerium M. So if you are using the low energy loss signals, its signal is more delocalized. So it means so if we have 1 angstrom probe, or if we have 0.2 angstrom probe, the ADF shape may change, but the chemical map, it doesn't change. Okay, so it's already governed by the signal delocalizations. So the point of my point is that we have no, as for us, there's no meaning to make it a smaller probe if the size of the atoms is already determined by the signal delocalizations. Okay, so then for the momentum resolved yield. So I will skip it because I have not so much time. But this is another way because we could get some information of the dispersions of the quasi-particles like exciton or phonon or plasmon or such kind of things. This is very important for the low-dimensional materials analysis. So yes, that's one direction that we have to go clearly. And for the energy resolutions, we have many different ways to go. But the one of the examples that we could make some molecular labeling, and we could get information of the carbon, or no, this is hydrogen isotope. So if you can make hydrogen, or if you make some heavy hydrogen that have two neutrons, so in this case you can get a clear map using the vibrational yield. So you could distinguish the stretch energy of CH and CD. So this is also the important directions for us to go. But the final example is something like what we could do with the time resolved spectroscopy. So this is our. Okay, so I cannot move this movie. Sorry. Oh, yes, I go on. So this is a kind of the in situ microscopy that the ion particles can can act as a catalyzer to grow the graphite layers. Okay, so as you can see, this ion particles is moving and they are making some carbon layers outside. So this ion particles eat carbon atoms and they makes the graphite afterwards. So this is a kind of the, how can I say, the in situ growth of the carbon nanostructures, but we can make some in situ EELS chemical map to EELS high resolution map to get the information from the ion particles. Okay, I'm coming back to this point later. Okay, so then, so also I have to, okay, it's too long. So, so this is an example of the chemical reactions. So this is, so we put some europium atoms in the carbon nanotubes, and they are moving around. But sometimes it's getting oxidized. Okay, so this in this case it's going out. So this becomes europium oxide. So we want to try to track this chemical reaction by spectroscopy because, okay, so oxidation reaction. So if you are europium metal, the EELS peaks will appear here, but it becomes oxide. You have the 2.5 EV shift. So we could track the chemical reactions happening inside the nanotubes. Okay. So this is the snapshot of what we have done for the analysis. Okay, so if you try to map the europium atoms using the EELS M5, so you clearly see the different europium, how do you call it, the state. Okay, so this is the map of the metallic europium atoms, and this is the europium 3+. Okay, so and this is the oxidation, oxygen came up. So once the oxygen comes into the structures, it makes oxide. But it's very interesting because if you continue to measure the electronic states, you cannot say which is metallic or which is 3+, because some atoms shows the both state. Okay, so this is the very interesting discovery for us, because if you have, at that time we didn't have very fast detectors, so we could make very slow mapping, but most of the europium atoms shows both state at that time. So it means, so only one atom stays 3+, and the other atoms show the mixed state. So this means, so our shutter time is not short enough to how do you call it, to track the electron transfer, because if we take one spectrum, it's always sometimes mixed, sometimes mixed. Okay, so this one is from mixed atoms, and this one is 3+, and this one is metallic. So if you have some sequential mapping, so it was, we could not completely track the reactions, but we see that some atoms are not how can I say, react as a chemical reaction scheme. I mean, they are sharing the electrons for several europium atoms. So this is quite interesting, but we haven't get some clear answer of this kind of experiments. Okay, then, okay, so this is how we interpret. So we are just trying to track the singular atom electronic state in a millisecond time resolutions or time intervals. So we could get some information which state that they have. Okay, so normally if you average, each atom shows two states mixed. So okay, so this is something that some information that how we could try to track the chemical reactions. Okay, so now I'm going, so finally, So this is a kind of the direction that we have to go for the time-resolved spectroscopy. Okay, then, so sorry. Now, finally, I will show our most recent results about the hybrid materials, or kind of the chemical reactions. Okay, let me go from this one. I think it's much easier. Okay, I'm going to finish in 10 minutes, okay? Okay, okay, thank you. Okay, thank you very much. So now, so we have started to track the chemical reaction of the carbon materials. So now we are selectively induce the chemical reaction inside the nanotubes. Okay, so we have now put some laser in the microscope, and we could put 4 lasers, but I just put, we still have two open slot, but we put 2 different wavelengths. And we could select the laser beam to laser energy to track the chemical reactions. Okay, so this is our very old figures in 2000, but once you put some laser lights that you can trigger the reactions. Okay, so this is the first example. Okay, so if you make some laser irradiations, okay, you can see these molecules in here, and they are also there, but only one tube can react. Okay, so the others do not show the reactions. This is the very important point, because each, as I told you, each nanotube has different color. Okay, so we can choose the right laser to activate desired carbon nanotubes. Okay, so if you have one specific nanotubes and you have a specific laser light, you can just excite the specific quantum object. Okay, so this is how we worked on that. So okay, so it's a bit long story, but I don't. So we have choose this 1.94 eV laser, and it just okay. In this case, only the I would say only the metallic tubes can be excited. Okay, so for the other tubes, it's transparent. Okay, so then so this is the very interesting results. So if you are using the metallic nanotubes, or if you're using semiconducting nanotubes, or if you choose the boron nitride tube. So boron nitride tube is a 7 eV band gap, so all the laser light can go through, okay? There's no interaction. It's completely transparent. So no chemical reaction happening inside, okay? So this is very clear. And for the metallic nanotubes, as I told you, for the metallic nanotubes, you just have exactly the same band gap at 1.94 eV. So it can, how do you call it? It can excite the reactions. Okay, so and for the semiconductor, it's very slow. The reaction happens is very slow. But for the boron nitride, it doesn't happen. So it means we could control the reaction happening inside the nanospace, because each nanotube has different band gap. Okay, so if you choose the right laser, you can activate certain nanotubes. Okay, then so now it's a bit too much complicated, so I don't say too much. But so we can track all the chemical state for during the reactions, because we are using the pulsed lasers and okay, so the spectroscopy has been done at each 3 pulse or something like that. So then, so we can get all the informations, because for the C60, okay, so this is 0-dimensional carbon nanotube. So you have all the electron, 0-dimensional carbon. So you have all the state like that. You can see, by the way, this has been taken from one molecules, okay? So then you can have some dimers, and you can have the trimer, and finally we can get some nanotubes, but this is 1-dimensional nanotubes with different Van Hove singularity, different discrete energy level. So, but we could follow all the small changes of the carbon KEH if we have some, how can I say, some monochromators. Okay, so this is a bit difficult for us because we try to push the possibility of the spectroscopy of the high spatial resolutions, high energy resolution, and also time resolution. So it's very complicated experiments, but once you decide what you want to do, we could do that. Okay, so this is my final slide, because as I told you, so for the spatial resolutions and the momentum resolution, I didn't tell you, but this is it's a completely trade-off. It's a Heisenberg uncertainty, so we cannot get both information at the same together. So, and the energy resolution and time resolution, this is also very much limited, because if you want to have some energy resolution, you really need longer exposure time or something like that. So, but we are trying to get some more, how can I say, more compromise conditions to realize such kind of the tracking some reactions inside the nanotubes. Okay, so this is one project we have been started, because this project is with the Austrian guys, and we are making some new spectrometer in Wien that you could get 1 millieV resolution with very high accurate momentum resolution. This is one direction that we are now heading for. Okay, so thank you very much. I think I speak too long, but this is my collaborator. So we have so many people to help us in Japan, and of course there's so many help from JEOL companies, and also there are so many visitors and many specimen suppliers. I should like to thank all my collaborators here. Okay, so thank you very much for listening. Thank you very much.